Swayam Prabha. Digital India. Educated India.
Let's examine that. So, the question is that if I know P and Q, then is it hard to compute D? This is your question. Yeah, so the answer is no. So, if I know P and Q, then I can compute phi of n as P minus 1 times Q minus 1. Okay, I am given E. Right. I run extended Euclid's algorithm. To get so extended Euclid's algorithm is an efficient algorithm. So, this it is a very simple, I mean we study it in school. So, it is a very simple algorithm which you know gives you this. It is efficient, I mean okay, simple, I should not say simple because it could be simple but still inefficient, but extended Euclid's algorithm is a simple efficient algorithm which runs in polynomial time in the input. Is it fine? Input length. Yeah. In fact, in the algorithms class we teach it, like it is one of the early algorithms that we study as an efficient algorithm. Very good question. So, you were worried about the fact that it may be running in time phi of n. No, you just run, so like you said, right. So, for input length m, it will run in time log m. So, I can find d in time log m by running extended Euclid's algorithm, right. And then once I have d, then it is just a matter of an exponentiation. But it is a good question actually. Let me ask you a different question. Why is exponentiation efficient? That is actually a good question. So, I told you that you know I want to compute y to the d. Now, d could be as large as n, capital N, right, where d is, you know, what do we know about it? It is less than n. ठीक है ना, so mod with n, so what? That just means that n is the upper bound. So, let us say even root n, or you know for simplicity think n. So, y, I mean how do I trivially compute y to the d? Y times y times y times y. Okay, so I will leave this as an exercise. Of course, you can do it efficiently, you do not have to do it like that. If you were needing to do it like that, you would really be in trouble, right, but yeah, you do not need to do it like that. Okay, good. So, this is the RSA assumption. Okay, and as the sort of the sneak peek is that RSA will imply trapdoor permutations. Okay, so basically if I define my function, right, like this, if I define my function like this, so f of x, if I define it as x to the e mod n, right, then using my trapdoor d I can invert this function. So, d will be the trapdoor. Now, I will define trapdoor permutations a little bit more formally, but the idea is just this. So, you know we have to be careful how we define them. So one issue is, right, how do we generate these hard problems? This is a really important question, because if there just exist hard problems, right, so for those of us who've studied some computer science, there are some problems which we believe to be NP hard. So this is kind of capturing like the hardest problems, in the class NP. If you don't know what NP is, it doesn't matter, but let's just say that it's capturing like the maximally hard problem in some sense. So why do we not use those for cryptography? One reason is that we don't know how to generate instances of the hard problem. So right, so remember that it is not enough to have a worst case hardness guarantee. It is not enough to say that there exists a graph for which the Hamiltonian cycle problem will take exponential time. This is not enough. I have to also be able to generate efficiently such a graph in order for me to use it in cryptography. So that is why I am being careful and treating it in this formal way, where I have a gen RSA algorithm, right. I have a gen modulus algorithm, which are giving me instances that yield hard problems, right. So the RSA assumption is not that there exists some modulus for which the problem is hard. The RSA assumption, the factoring assumption, these are that there exist algorithms which can efficiently generate problems which are hard. And we really need this in cryptography, which is actually at the heart of the problem, the quantum problem. The fact that we need this efficient generation, among other things, right, we need to generate efficiently hard problems. We also need to generate sort of, in some sense, pre-solved instances of the problem, because at a very intuitive level, like there needs to be some kind of trapdoor or some kind of decryption key, or some secret which lets me invert or get some functionality at the end of the day. So if I think of that as generating pre-solved instances of a hard problem. So note that this gen RSA is giving me a trapdoor, right. If I were just generating a modulus, would that be of any use to me? No, right, because obviously even I can't factor it. So then sure, you also can't factor it, but so what. So generating these pre-solved instances of hard problems efficiently, this is actually what forces cryptography to rely on problems like RSA and factoring, which have algebraic structure, right. They are not unstructured. I mean, like a NP hard problem is much more unstructured, like the 3-SAT problem. If you have seen the circuit satisfiability problem, what is the circuit satisfiability problem? If I give you an arbitrary circuit, right, find a satisfying assignment. So what have you all seen this problem before? I mean, I am sure some of you have, but for those from physics and so on, maybe you have not. So if I give you a big circuit, right, and the circuit has various gates, there is lots of stuff going on here, right, these are all the inputs, there is one output, okay. A basic question is, so let us say the output is a bit. A basic question is, does there exist some input which gives me the output bit 1? This is the satisfiability problem, circuit SAT. Now what is a trivial way to solve this problem? If I do not care about time, check all inputs, yeah, 2 to the n of them. Exponentially I can solve it trivially, right. Turns out that for an arbitrary circuit, note the use of the word arbitrary because it is very important. For an arbitrary circuit, I do not really know how to do better than that, okay. Now of course there may be some circuits for which it is not hard, right, like there may be circuits for which, in fact you can easily construct circuits where I start at the output, right. Let us say there is just one gate below that, let us say it is an AND gate, right. So then that means that the 2 inputs to AND will be 1. Now let us say those feed into other AND gates, then you know the inputs to those will be 1. So there are obviously some circuits where you can solve this problem very easily, right. But for an arbitrary circuit you have no good way. But now how do I generate a circuit for which this is hard? This is the problem, right. I do not know how to do that. This is one of the big open problems in cryptography. Okay, I do not know how to do that. So therefore, in cryptography what we do is that we choose problems that sort of have more structure. So they are not NP hard. I will not go into complexity classes and so on. They do not, their hardness is not very well understood from the complexity theoretic perspective. So we end up choosing problems that have some kind of structure, and they are not as unstructured as like an arbitrary circuit SAT problem. They have some kind of structure, and actually that is where quantum computers sort of, it is a very unfortunate matching, that like the structure that we have been using here is exactly the kind of structure that this one superpower that a quantum computer has, which is of efficiently computing a quantum Fourier transform, right. We have not studied the Fourier transform in great depth yet, that will be after this, right. But we did see examples where I told you like we are computing the Fourier transform by applying the Hadamard N gate and so on. So this is that one superpower that a quantum computer has, which is that it can compute this Fourier transform very efficiently, which a classical computer would have needed exponential time for, and it so happens that these problems, when they succumb to this extra power. So it's in hindsight it's actually quite natural. Of course, we are not dead, because we can choose other types of structure from which we can build cryptography for which we do not know how to use the quantum Fourier transform. Does that make sense to everybody? Okay, so good. So this gives us trapdoor permutations. Actually, I am wondering if it's going to be worth it to define this one way function trapdoor. Okay, maybe, okay, I will take a middle path here. Okay, so I will get a one way function from factoring. Okay, so basically f of x y, right, if I just compute x times y over the integers. Okay, this is a one way function because it is easy to compute and hard to invert. I will maybe very quickly go over the formal definition of one way function and so on, but maybe as we see the assumptions also it is useful to just see what they give us. And by the way, like a one way function is sort of the weakest assumption you can make for cryptography, right. So the existence of a one way function we do not know how to prove. In fact, if we knew how to prove that, then we would be very rich, because that implies a solution to the P versus NP problem. Okay, so the existence of a one way function assumes that P is not equal to NP, but it does not follow from that. So it is an additional assumption on top of that. But this is like the weakest thing you can assume if you want to get cryptography. Like asymmetry is one of the basic tenets of cryptography. It is the basic thing that you would need. Nevertheless, even though it is, as I am saying, the weakest thing that you can assume, it is actually already useful. So can anyone think of like a, do not tell me encryption, okay. So encryption will not work from one way functions, but at least not in the way that you will think of. But can anyone tell me like a natural real world application of a one way function? No, that is not correct. The answer was that we can initiate a transfer for Bitcoin, but we can't get it back. So this is think of something simple. Actually what you said, it does not It doesn't translate to anything even meaningful, because when we say I can transfer a Bitcoin but I can't get it back, what does that mean? I mean, I can send a transaction, right? Of course somebody can send it back. So the idea is that I don't know, I mean, there are various security properties you can look at. Like if I make a transaction, let's say, 5 Bitcoins from me to Anshu, let's say, right? Of course, I mean, that transaction can be sent back to me, but it doesn't have any meaning. I mean, so there are multiple other things you might want, that Anshu should not be able to change the number that is certified or whatever, or you should not be able to change Anshu's name to your name. There are various other things you might want, but no, this is not a good example. Something else, something simpler. Like a very simple idea is, if I am a server, and different people have accounts with passwords. So one simple idea that might use a one-way function is that I store the f of your password with me. So I don't want to store all your passwords because that is insecure. It can be insecure. I mean, I may not myself be trustworthy, or well, I guess if I am not trustworthy, then all bets are off here, but because you will send some password, right? So if I wanted to, I could store them, but let us say that I don't want it to be visible to others and so on. I can store f of your passwords, and now when you authenticate yourself, I can just compute f of whatever string you gave me and check whether that matches what I have. That is a very toy example. That's true. So the point he is making is that there better not be collisions. So it shouldn't be that like if I am just willing to store 1 bit for each person, then there is a big problem, right? Because if I am only storing either 0 or 1 against your name, like if I am just computing the sum of your digits mod 2 or something like that, then obviously there will be a lot of collisions. So that means multiple people's passwords will hash to the same thing. So anyway, that would not be hard to invert, I guess, the example I gave. But the yeah, I don't want to belabor this particular example too much. It's a toy example. I mean, in reality, you would be doing more stuff for authentication, but a natural idea is that we may be storing one-way functions of the password. And this thing about collisions that you mentioned, in a way, so yeah, like there are more advanced notions like collision resistant hash functions and so on. Yeah, I don't think I want to go into this more. The question is, what if two people in the same family have the same password and don't know it? So first of all, I mean, I don't know if such families exist which are so harmonious, that people are choosing the same password. Secondly, yeah, that is actually not even an attack. Because this is outside the model. This is bad behavior which is just outside the model. So if everybody in this class, chooses the same password, for whichever reason, I don't know, Fourier transform or something, then there is no solution, there is no security in that setting. So the security of a password based authentication scheme only comes in if passwords are well chosen. If you choose your name as your password, then there is no security. I'll just answer this. So the question was that, in some recent company, some test or something, everybody had the same password. So yeah, I don't know what is the threat model there, but if it is the case that the whatever you are storing using your password, if that is supposed to be secret, and if the user IDs are not secret, like if it's your S-mail ID, then it's a trivially attackable thing where you can log in with somebody else's username and get some information you are not supposed to. So now I don't know what was being stored or what was happening there, but yeah, generally having the same password, I mean, maybe in some very short like test environment, like if for 3 hours I need to log in and give a test or something like that, maybe there is some setting where it is okay, but yeah, by and large this is not okay. Okay, good. So where were we? Yeah, we were on the RSA assumption, made fairly slow progress. Let's see. So yeah, so I wanted to talk a little bit about the RSA and factoring assumptions. Actually, in the interest of time, I won't do one thing which I had originally hoped to do. So we already discussed how, if I can solve factoring, I can solve RSA. What about the other direction? The other direction doesn't hold. Okay, so it could be that RSA is weak and factoring is still strong. But one of the things that can be shown is that recovering the decryption key or the trapdoor for RSA, this is as hard as factoring. Okay, so there is a very cute proof for that, but maybe I will just refer you to the book and not go into it too much in class. It will not be relevant for us. Okay, now the other family of problems I wanted to show you were, this discrete log based problems. So let us very quickly define that. Okay, so discrete log, so far we got a one way function and we got a trapdoor permutation. By the way, of course, we have not defined these trapdoor permutations rigorously, we will do that. But notice that this function is from Zn star to Zn star. So you have to still establish it's a permutation, but at least the domain and the range are the same, which is a minimum thing that you need.